or for us to actually do in the future, because we're still fixing on these kinds of things. So what the hell did they want us to build? They wanted us to build an ad network, but not just any ad network. An ad network would be called via REST API, like every other REST API ad network out there. Clients would provide us with a location, in MySpace, Facebook, or Twitter user ID, and whatever posts a user would see. Because it turns out that our ads were going to be shown as part of a Twitter client, or a Facebook client, or a MySpace client. And we wanted to return ads very quickly that were relevant to the content that the user would see, as well as targeted to their location, and in particular to their user ID if we have some history about them. You can think of it like AdSense for the stream, where the stream is this nebulous thing that real-time microblogging is being called nowadays. So who were we competing with? There were a few different places that we were competing with directly. A company called AdMob, which was purchased by Google, which are in basically every mobile application out there nowadays. 140 Proof, which is can't remember where the heck they were located, but they were doing almost the exact same thing we were. And then RiotWise, which more or less ended up doing links to New York Times, things like that. Plus, some dozen or 2 dozen other companies, some of which have gone out of business, some of which are still around, that I don't remember because we got out of this business. I'll explain why later. So what did we use? Well, we used Amazon EC2 for hosting. We used a bit of HA proxy for load balancing. We used Redis for almost everything. We used Apache ModWiseGuy for our Python servers. Obviously, we used a bit of Python. We had used RabbitMQ for a brief period, but it turns out that RabbitMQ had some issues in that it would crash if you wrote too much to it. And for us, too much to it was 200 to 300 messages a second, which is kind of preposterous. So we moved on to ActiveMQ, PostgreSQL, MongoDB briefly. Again, we overloaded it. We didn't quite use it right, which is why we had issues with it, but I'll get into that a little bit later. We use syslog-ng for all of our logging stuff because it's awesome and improves upon standard syslog in many ways, and a lot of different libraries and utilities to plug all this stuff together. This is what we built. This is the ultimate destination. Don't memorize it, it's okay, we'll work up to it. So we built a lot of software. Oh, go ahead.
Do you take questions in the living talk?
Absolutely. Also, I totally forgot to mention it, but I received a Starbucks gift card the other day for doing something special. I have no idea how much money is on it. If you ask the most questions, or I like you the most, you get it. All right, ask.
So I recognize all those components except Redis. Can you briefly tell us what that is, please?
Absolutely. Redis is a remote data structure server. You can think of it like Memcache on the most part. You can store keys and values, but not just keys and values. You can store keys mapping to a list, or keys mapping to a hash, or keys mapping to what is called a sorted set, which is basically a hash but is sorted on the values.
Okay, how does that compare to Postgres?
So it's completely different in every major way. So Postgres is a database, right? It's relational. You've got tables with columns and rows and things like that. You add indexes, what have you. Redis is strictly a data structure server. So if you've got, say, a hash table that you want to map from, we've got a hash table that maps from user IDs to their location. We have that as a single key in Redis, but hanging along next to it, we've also got keys that represent counters, and keys that also map from, say, user IDs to the gender of the person, or user IDs mapped to any one of a number of other things. So you can use it on the list side of things. You can use them for queues. You can use, there are many, many things. I've got a few blog posts about it. It's out there. Yes, so Postgres is fundamentally limited by how fast it can write to disk. So if you're bulk writing to Postgres, I mean, if you can get a few hundred writes per second on a single disk, you're doing pretty good. You can do bulk writes to it and maybe get a few thousand. Redis typically will do 100,000 or 200,000 because it's all in memory. That's the big difference. It's all in memory. It does have persistence options to write to disk, but primarily it's an in-memory data store.
Did you use any persistence options?
Absolutely. The particular persistence options we used because we were okay with so we use many persistence options now. In this case, because the data wasn't necessary to be there all the time, and I'll explain why later. We didn't really use any persistence options because we saw the database is holding the one true data, and we synced from the database to Redis any data that we wanted to be there. And anytime we updated the database, we also updated the Redis.
So is it like a cache?
You can think of it very much like a cache, yes.
So you do not use persistence options?
Not for this, no, but
Other stuff you did?
yeah, we use Redis for almost everything. Well, not almost everything, but we use it for many, 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 many things.
So did you say you used it needed a cache and did it for the fast line?
Not just for cache. I mean, we use it for a primary data store now for some other things, completely unrelated to this ad network that we turned down. All right, so onwards. So software we built for the ad network. We built a mini Django-like layer for WiseGuy handling and request routing on the Python side, and actually that was written by our own Jeff Skank here, who's here. Basically, Django wasn't fast enough and was very, very laggy as a framework when routing requests, even when you don't have any middleware. So rather than having to deal with that, Jeff manned up and built one for us. And we still use it today, even now for our role expansion stuff, for the other parts of our business. And it's fast, it's furious, it's great. We also had written a Stomp protocol driver for Twisted to handle brokering between our ActiveMQ queuing system and the Python side of things, which is written by one of our senior devs, Eric Van Duostein, who's not here today because we don't bring all of our dev team to our meetups. And this was written because we had been coming off of Reddit or RabbitMQ, and we had been using ActiveMQ with the standard caret bindings in Python. And there were some issues where ActiveMQ wasn't disconnecting sockets due to a bug which he ended up fixing. Thank you. So he built a layer to handle all of the connection stuff so that we wouldn't end up having sockets build up, and then watch ActiveMQ explode. Also, we built a complete Celery-like task server for ActiveMQ in Python, also done by Eric. It's totally kicked ass. We still use it today for basically all of our task serving needs. So if you have a task queue or whether you or your developers have any task queues where you, rather than using cron on a handful of boxes, you instead have a bunch of workers that pull tasks off the queue. This works great. Also, we briefly built an object Mongo mapper that was basically a layer that converted from a data structure, or at least types very similar to SQL Alchemy and Elixir, into the data format that Mongo handles. At the time, it was about 2 to 3 times faster than any existing mappers. And we stopped using it because we stopped using Mongo. Explain why we stopped using Mongo later. Basically, it boils down to we weren't using Mongo the right way, and to use Mongo the right way would have been too expensive. We also built a geocoding server that takes latitude, longitude, and a few other different things and maps them down into region, like the Los Angeles region, New York region, as well as state and country for any latitude, longitude on the planet. And this was useful for ad targeting because we did location-centric ad targeting. We also built a content categorization engine. Very simple method, but it ended up being a little bit slower than we wanted to, and by the time we made it fast enough to really be useful, we realized that there was a lot of other things that we could do to improve the bottom line, and so we just got rid of it. We also had a Redis-based real-time counter server whose counters were relayed via syslog, and that is because, like any other piece of infrastructure, Redis could go down, and so relying on something to connect to this service and write data to it, and then disconnect was a point of failure, and we had machines go down, we had Redis fill up available memory and get killed by the Linux out-of-memory killer. And so we relayed via syslog because, at least when you're sending data to UDP, it can't fail. We also built a complete ad targeting system based on Redis set and zset, that is scored set, unions, and intersections. Turns out that everything we needed to do could be encompassed by a couple simple Redis commands. This is great for us. It meant less software that we needed to write, and it turned out to scale very, very well. So, how would an ad request come in and come through? Here is a worker box. We called this a Rambo architecture. And I'll jump back to an earlier slide later. But basically, this was a worker, and it could continue running more or less regardless of what the rest of the system ran into. So, a request would come in from our HA proxy load balancer and would be relayed off to our WiseGuy Python web server on the local machine. The server, the Python API server, here, my mouse is in the way. This guy would look at the content, analyze the content, geocode the location, prepare the proper set of ad targeting calls into Redis over here. Redis would do the targeting. We would pull the cached ad information from that same Redis. We would send the response off to the client, and we would take anything that needed logging and throw it off into ActiveMQ. And then our Python task server down at the bottom would aggregate any sort of log data over the course of a minute. We would typically pull 100 messages off at a time, aggregate them, write the data off to Postgres, and update any necessary rows. When a impression pixel would come in, the request would come in, and many of the same, go for it.
The question on that last slide is, so ActiveMQ, that's a queue, right, for
Yes.
tasks?
Yes.
So what action do you take after you've served the ad?
After we've served the ad and sent it to the client, we would take whatever logged information that we'd like to log. All of it was logged off to syslog, but sometimes it would require a little bit of extra processing for one reason or another.
Like to bill or what?
Sometimes bill, yes. Usually we would handle billing a little bit later, either at the impression side or the click side of things. I think occasionally we wanted to see, okay, so we totally served this ad. Early on we were logging everything to Postgres as opposed to using any other logging thing. So it used to be that every request that came in was logged off to Postgres, so that's where that would happen. Later on, it was more or less just, yeah, so we totally served an ad against this guy, so just put that in the queue and just report that we've served this particular ad at some point or another.
If something takes it out of the queue, that's something, right?
Yes, the last one. The Python task server pulls items out of the ActiveMQ instance and aggregates as necessary and writes to Postgres.
Oh, okay.
Yeah. So one of the magic things about this particular architecture is that the server, our Python API server way up at the top, he doesn't access the database at all. Every bit of data that he accesses is from the local machine, whether that's Redis, whether that's the geocode server, or whether that's spewing the result off to ActiveMQ or sending a log off to syslog. He doesn't touch anything, so even if network troubles arise, whatever, he doesn't care. Now, obviously, if the response can't get back via Apache, well, that's kind of a problem, but then he probably wouldn't have gotten the request in the first place anyways.
So presumably HA proxy is doing some health check to this API server for some resource that pulls behind it. Like what if something funny happens because funny things happen and
Yes, absolutely.
code dies on localhost, but Apache was responding?
So our Python API server would make requests to, say, the geocode server in that particular case, and it had a deadline. If it didn't receive a response from the geocode server within a brief period of time, it would actually just ignore it. So we wouldn't have location targeting information. It did have some local lookup tables that it could look at. The geocode server handled the entire world. It also had some generic information about the United States available locally. So because 99% of our requests were for the United States, if it failed to get a request or failed to get geocode information for, like, say, Fresno, California, it would instead say, well, check to see, is it probably in the United States? If it's probably in the United States, let's just target a general ad for the United States. Farther up the chain, HA proxy actually does checks to determine whether or not API servers are responding slowly. So it actually checks latency on a per machine basis and automatically says, okay, so this guy's slow, so we're going to send less traffic to him and put other traffic to other places. It would do all of this automatically, and it worked very, very well for us.
So at this point, is ops getting paged, or at this point, do you have enough trust in the robustness of the infrastructure that with that large data set that you're going to keep in memory, you're going to get by okay?
Sure. So in this case, we didn't care about this box. If this box goes down, we don't care because we've got 10 of them, or we've got 20 of them. And we live by the redundancy. So the title of the talk is Building for Uptime, Expecting Failure. Any component of this box could die. Say the Python task server could die. You know what happens? You just don't process events for a while. ActiveMQ dies, well, then the Python API server can't write to the events, and so the Python API server dies. So then Apache requests can't come in, so HA proxy stops sending stuff to it. Redis could die. Well, then Python API can't send stuff to it. No big deal. If the geocode server dies, well, then we're not geocoding, so we're just doing a general ad target. So,
Is there just one geocode server?
say again?
Is there just one geocode server?
There's one geocode server per box.
Oh, okay.
Right. Everything is local. We do have a generic geocode server that the other parts of our system do access directly. That's got one, but one per box. And this particular geocode server, which I think is arguably the most innovative part of it, we stored geometry data for the entire planet in about 300 megs of memory. And if you've ever seen that data, it's fucking huge. So I was very, very happy with that.
The geocode server, was that lat-long based or IP based?
We had a bit that did IP-based stuff, so we could do IP-based, but we also did lat-long. We did both. I totally should open source that. Then I can use it next company too. Okay, so an impression pixel. So when an impression were to come in, again, it comes in through HA proxy. The server decodes the request, sends the response, and logs the impression to ActiveMQ. It's red because this changed from the last slide, but this is the same. Python task server aggregates log data and writes to Postgres. In the case where we would bill for impressions. This was very, very rare. Most of the stuff that we were doing was per click. But in the case where we would bill for that, you know, as part of the task server, it would decrement whatever pennies necessary, update the database, and if an ad were to fall out of the network, it would write to the Redis. I should have had another slide that shows the entire network again, but I'll jump back to it in a second. An ad click, same stuff, load balanced. The server decodes the requested short URL, fetches the destination URL from Redis, returns a redirect response to the client so that the client can get the final destination, and it logs the information about the request to syslog directly. And I'm explicit about it here because this is very important for billing for us, because you like to have one true source of data, and for us that was Postgres. But being able to validate that with something like syslog is also very, very important. And then we had the Python task server aggregate right to Postgres, and then if an ad is run out of money, it would take it out. Go for it.
So you're talking, there's syslog, there's ActiveMQ, and there's Python. Sorry, and there's Postgres. So do all three have the same information, more or less?
So syslog basically captures unaggregated information in log files and just plain text files that we gzip and send off to S3 for archival and analysis purposes, searching, you know, finding out, okay, so who are all the people who clicked on this thing because we want to de-spam them. We want to find out who clicked 10 times, things like that. ActiveMQ would only hold things as a transition from the Python API. It would log to ActiveMQ. Everything in ActiveMQ would eventually be flushed out to the Python task, which would write off to Postgres. So really it was just Postgres and syslog. ActiveMQ would just be a transition. It's
Yeah, the slides are confusing.
yeah.
Well, two cents when we do metrics collection at Order Slow, we compare it to syslog in part because we don't always trust it. So we log an event when we write. So we use Memcache. When we write to Memcache, we log an event. But just as a sanity check, we cross-reference and we make sure that the numbers are complete. Just because it gives us a slightly trust. Like, luckily for us, we haven't had a problem yet, but that makes me feel better when we pass that number.
But you're using Memcache as some persistence feature, I guess?
Yes, and we also constantly query it as part of our applications to collect data for our integrity too.
Have you lost a Memcache instance or a Memcache chunk of data yet? Has that happened?
Yes, and
Does it happen a lot or does it happen once?
so it happened a couple of times. So it happened twice, and our application server didn't fail the way we expected it to, which was a Memcache module in Ruby. And we ended up having to upgrade that module, and then we realized we made a mistake that
Okay,
we had to trust.
and then you just have to get caught up from syslog.
Right.
And that's the same thing you guys do with this.
Basically, if something nasty were to happen to Postgres, then at least we'd have the logs and we could recover from that. At least we could recover billing. At least we could recover, you know, yeah.
Did you ever have to do that kind of validation?
No. Thankfully, we got very, very lucky. Our Postgres server never died on us.
Did you test it? Did you test it actually works that you could like, you know, zero out for low ends? It's an interesting idea, but it's like it's pretty complicated.
Absolutely. So we didn't run it for that. We ran it in the case where we had one of our clients that were placing our ads, who we sent a check to, and he said, "This isn't enough money." And we said, "Oh, really?" And he said, "Yeah, really." And we said, "Okay, well, let's pull down the logs for this month." And so we pulled down the logs, and because at the time we had it all in Mongo. I'll get to that later, but we got rid of Mongo. At the time we had it for Mongo, and we actually had a column that was indexed on, you know, the particular developer account that would receive the money. And we pulled down all of the requests, all of the impressions, and all of the clicks. We pulled them all down. At the time we were logging to Mongo, also through ActiveMQ, as opposed to syslog. And We pulled all that data down and we said, okay, well, so these calls led to these impressions, which led to these clicks. Oh, hey, guess what? Some X number of these clicks are duplicated. He was counting duplicated clicks. We were counting deduplicated clicks. And so we said, hey, so it turns out that a lot of people were were clicking on something, hitting back, clicking on it again. We're not going to pay you twice for that same click for that same guy. And so after we sent him this information, and after we went and dug in and said, well, also some of your claimed clicks, the person changed IPs. And the particular IP change was, or location change was from like Nevada to Indonesia, or Nevada to Romania. And, well, yeah, it seemed to us like somebody was debugging on their device and clicking through, what have you.
How do you know it's the same click?
Because we would generate a unique URL based on every ad that was targeted received a unique URL. We didn't store that because that would be silly. We packed a bunch of information into a 20-byte URL and we encrypted it and signed it. So when we got it back, we could verify that it had the information, it hadn't been tampered with, and we could get exactly what we wanted. And, you know, yeah, we used AES and worked great for us. AES.
Oh, it's a hash.
No, we use AES for encryption, and then we used a prefix of SHA-1, but we used our own private key. So the combination of AES, because we hash based on the encrypted data, not the decrypted or the decrypted data. So yeah.
Did you ever figure out why that might be?
So not definitively, we just believed that either they were debugging, they were traveling, like they had opened up their Twitter client at one time, you know, turned off their phone, traveled, opened it up. That happened once or twice because there was a many-hour delay. And we also included timestamps for validity, and so we wouldn't charge the advertiser for it, but apparently the client would count these things.
In terms of establishing an identity user, it was just a vanilla cookie, right?
Say again?
It was just like a vanilla cookie in terms of like identifying who the user are.
No, we didn't use cookies. It turns out that the combination of, so basically every browser on mobile and every browser on desktop and every client wherever sends you just enough information, combined with the fact that we had their username from whatever network, right? The combination of username plus whatever browser information that was submitted was sufficient to more or less have a unique identity for everyone who made a call. Combined with the fact that an ad call resulted in a unique identifier for that particular ad call, we can actually chase back to the original ad call that was provided. Along with every impression pixel has got basically the exact same thing, only with a .jpeg attached to it, or .gif. Yeah, .gif, because that was smaller. And then the short URL was basically the same thing, only, you know, something else. So we could always chase back up the tree. All right. So what could go wrong? Turns out just about everything. Postgres could go down, but we're okay. Postgres goes down, then we stop updating, we stop writing to Postgres. Our task server stops running, and the queue just fills up. That's not a problem. We bring Postgres back up, we turn the queue back on, and we get back up to date. Now we could conceivably serve ads that shouldn't be served. Because they ran out of money, and we just didn't know that they ran out of money. Conceivably, we could have received new ads that we're supposed to target, but because Postgres was down, we didn't write to Postgres, and because we didn't write to Postgres, we also didn't write to our Redis master. That was okay too. If you're not serving an ad that should be served, well, you're just not making as much money as you should. If you're serving an ad more often than you should, that's kind of a problem, but we actually budgeted on a per hour basis instead of a per 24-hour basis. and we automatically adjusted the value of a particular ad so that it would typically spend over the course of an entire hour. So even if we weren't upgrading Postgres, we could typically serve those ads over the course of the duration of an hour, and it would have the money, even if we weren't updating it.
This is really interesting because the value of what you just described seems like that it's worth it to do that what you just said versus do something like slowly and fail over for Postgres.
Yeah.
Did you actually make that decision explicitly?
So when we were putting this out, we were developing against Postgres 8.4 because Postgres 9 with hot streaming replication hadn't come out yet, which was fine. I mean, we were using the tools that we had. But we had to be cognizant of the fact that EC2 instances died. Occasionally, sometimes very often, it happens. So we had to remember that. And so we also had to be cognizant of the fact that we needed to have layers at every point that if something down the line died, that layer could die and things above it would still be okay. You know, something else up above would be okay. This just happened to fall out of our Rambo architecture. Like this thing can continue even in the face of failure, you know, like everybody's a Rambo in this case. Every little bit is Rambo. Even the entire machine is Rambo, you know?
Slowly's hard. It's really hard to replicate those.
Yeah. We never.
Well, like in a failover too.
Well, you guys weren't replicating, right?
No, we weren't.
Just didn't care.
Yeah.
Well,
Yeah. At the time, we didn't care.
You didn't care because you had just many.
Well, in this case, the particular Postgres that we were writing to, it was also the Postgres that held all of our, you know, money information and all of our main admin website information and things like that. We kind of hoped for the best and totally got lucky because that database machine has been up for basically a year. We're switching over to Postgres 9 in the next couple weeks with the hot streaming replication.
I'd like to clarify or expand on these remarks I made about Sony being hard. We're on Postgres and Sony website. Sony is pain in the ass to administer. But it works and it's great and it's very powerful. It gives you more flexibility than even built-in replication in Postgres 9, even partial replication.
And then you can keep the right hand on. So that's a real idea, right?
it's theoretically awesome. I totally agree.
Yeah.
Like it's an awesome architecture.
Yeah, there's other things you can do, like you can have a replication chain. You can have multiple levels of replication. So, but if you can not have to deal with administration of Sony, then that's great.
All right.
SLOMY. It means elephant in Russian. Symbol of Postgres.
So I'll jump back to the diagram in a few seconds. But basically, when all of our Redis servers on each one of our API servers slaved off of a master Redis. Redis offers a master-slave replication setup. And so when we wrote to Postgres, we would write to the master. And the master would automatically replicate to all of our slaves, typically within a few milliseconds. So our Redis master could go down, but this wasn't a problem. Because Redis slaves, when the master go down, just keep all of the data they had before. They don't drop the data. They only drop the data when they reconnect to the master and resync, and then they're just generally unavailable until they get the data back. This wasn't a problem. We actually ran into a Redis master failure at one point. That particular issue was caused by a shoddy network connection between our master and one of our API servers. It had been buffering up over the course of days, and we weren't paying attention to our muning graphs, watching memory increase on the master until the out-of-memory killer killed it, and then all of our slaves were serving ads. We didn't notice because we were serving ads continuously through this. And it was only because somebody said, hey, wait, I'm looking at the graphs. I think it was probably Lars, like, I think the master died on us. And so we hopped on, and lo and behold, it totally did. Or it was about to die, or something like that. So what did we do? We brought up a new Redis master. We synced data to it. We pulled a machine out of the load balancer, reslaved it against the new master, waited for it to get updated, and brought it back up into the load balancer, and we continued on one at a time. And we swapped everybody over. We killed the old Redis master. Problem solved. Yeah, this really wasn't a problem. Just, sometimes stale data, just like the Postgres problem. But what about if an API server went down? Well, that's not a problem. We've got other API servers. We don't care. In the worst case scenario, because we had a cron task, so it's like cron, only it runs in our task server, it ran about every minute that synced all our data off to Postgres and Redis. And maybe we would lose a minute's worth of requests. Cost of doing business. HA proxy could go down. This is where we had a problem. It turns out we had a single point of failure, and that single point of failure was HA proxy. I'll jump back. Oh, there we are. So if you remember our diagram here, so we've got a Redis master, we've got a Postgres. They can die, no problem. Any part of the component inside of the API server, including the entire API server, could die, and we'd be okay. But we've got a load balancer. If that went down, we're kind of boned. We got fairly lucky in that I believe at the time we hadn't been using EBS, so even on EBS failures, HA proxy was okay. In addition, because it would never read from disk, once HA proxy was up and running, it was up and running. We did use elastic IPs for it, so maybe you get a 5-minute swap over. We also had a very short TTL DNS, so we could even use DNS and DNS propagation to help us there. I'll talk about some ways you can make that better in a second. And we're back to where we were. So, what are some ways we can improve this thing? Because there were problems with it. So, the first thing was because our request would come into HA proxy, and HA proxy would make requests off to Apache, there was a remote connection there. And though HA proxy buffered from slow clients, technically speaking, anything not local is a slow client. Adding a layer of Nginx on the local machine to buffer between our WiseGuy server, whatever that is, and the remote machines can make a huge difference. I actually talked to a guy last week. He called me about the blog post that this talk is about. And he asked, hey man, read the blog post, we're doing a lot of the same things, can I get some advice? And I told him about this, and he said, we just did that. We just added Nginx between our ad server and the remote world, our load balancer. And that doubled our performance. Just that one little thing, because your sockets aren't being tied up sending to some remote machine on some whatever network. Nginx is that good. For those of you out there who have been doing load balancing, you could use HA proxy and you could hope for the best. I would instead recommend ELB. We didn't use ELB because we had a concern that perhaps requests would come in that we wouldn't know about, that they wouldn't tell us about, that it would fail on their side of things. HA proxy would solve that. There was also some features that they now support that they didn't support, having to do with DNS records. They support it now. If you're using it, you may want to try it. If you're okay with the potential that they're silently failing. Also, if you're running Python and WiseGuy, consider switching to a server called uWiseGuy, or I call it MicroWiseGuy because it makes sense to me. What else would U stand for in this situation? Instead of Apache and ModWiseGuy. It's fast. Oh my God, is it fast. The only thing faster than MicroWiseGuy is MicroWiseGuy and Nginx. No joke, for serving Python. Nothing is faster. There are benchmarks. It shows that it uses a small constant amount of memory combined with Nginx's small constant amount of memory, and it's magic. It's fast and it's small. Instead of using Django, or instead of writing your own as we did, at the time there was nothing else that offered what we needed. Nothing that was fast enough, nothing that was small enough, so we wrote our own. I've been using Bottle PY, which is a micro framework for basically doing WiseGuy request routing. It's awesome. I'm getting 300 microsecond hello world responses through MicroWiseGuy and Bottle on a virtual machine running on this laptop. I can't get 300 microsecond ping times to the virtual machine on this laptop, and it's able to get that kind of performance. So yeah, use Bottle PY if you need something small and you need it fast, and you can plug it in with the rest of the stuff. Also consider replacing ActiveMQ with Amazon's simple queuing system. Just because it's there, it's available, it's relatively inexpensive. Sometimes Amazon's SQS can be high latency. That's why we didn't use it. Also, Amazon's SQS is basically put stuff in a queue and that's it. We wanted to be able to delay tasks. Alternatively, you could use a second Redis, and there are many libraries for doing this in just about any language. For building a queue on top of it, I built one myself, planning on open sourcing it. First, I need to use it in production. Alternatively, if the particular uses are more of a publish-subscribe nature, you want to just broadcast this event to many machines, even 0MQ would work for you, or could potentially work for you. It's very, very fast, written by a group of very smart people. Consider using it. Also, if you're doing Postgres, use Postgres replication, or even consider Amazon's RDS. I see some thumb downs and some booing. I would recommend trying it to see if it actually works for you. If it doesn't work for you, don't use it. I've heard some nasty latency things. I've heard some concerns about the fact that because it uses EBS, whenever EBS is hokey, which is what, daily, weekly, sometimes that your databases can be kind of funky. And those simple DB is very simple if you want Cassandra-like thing or whatnot, or I don't know. Yeah, if you want a Cassandra type thing, you can totally use it if you can fit your application in there. I've also heard some concerns about latency, although it's supposed to be able to scale hugely. Ultimately, though, your Postgres box will probably be more expensive than an RDS or a simple DB setup.
Why the hate towards MySQL Master?
I don't have any hate for MySQL Master, except for the fact that I've got a bit of hate for MySQL. And
Or MariaDB. Like you can mix it up.
And which one?
MariaDB for the post. You say that as you do. Percona is a sponsor. Monty, who was one of the founders of MySQL, ended up leaving MySQL because he said fuck MySQL, fuck Oracle, and it started up MariaDB. So
Yeah.
it's patch MySQL with all
Yeah.
their kind of DB magic.
So I guess to explain, my hatred for MySQL is, well, actually, Amazon's RDS is MySQL.
But there's no replication.
You can add, well, yeah, you can pay for the extra Oracle.
Scary.
Yeah. So you can get replication. You can pay extra money, and they'll do multi-master.
Right, but there's no binlock Minecraft on side control.
Sure.
And you can't
Yeah.
relay RDS from another master.
Exactly.
Yeah. There's. Yeah. If you can fit your stuff into there, use it. If you can't, that's fine. I guess my personal hatred towards MySQL is that it took them a long time before they actually had ACID capabilities, and everybody else in the marketplace had them for years. It's like, hey, you can write it, but it might get there. You may not have that data later. And I've been bitten by that years ago, and I've emotionally not recovered from that data failure. More monitoring. I don't care what you do, you don't have enough monitoring. The only time you have enough monitoring is if you have 30 graphs per box, and it's all jacked into your head, and you are monitoring it 24/7. Until you get to that point, probably not monitoring enough. We don't monitor enough, even though we add more and more every week. Also, more alerts. We don't alert enough. I know because we've had stuff fail. And thankfully, our stuff is written so that if it fails, it's okay. We wake up in the morning, whatever. We have gotten monitoring and alerting that has gotten much better since Lars joined. I need to instrument my stuff better so that we can add more alerting and monitoring. But ultimately, I'm not the one getting paid, so maybe I shouldn't be saying more alerts. Lars is, and I'm sorry, Lars.
I think instead of more alerts, it's more better alerts.
That too.
Because like I've been in many situations where I made more alerts and then everyone ignored them. So they actually have inverse value.
Yeah,
They start to go down if you make more of them.
absolutely.
Whereas if you spend twice as much time figuring out how to make a better alert that actually tells you when something has failed, then people who get it will take it seriously and will actually work. But it's really hard. It's not a science. It's a hard approach.
Definitely. It's a good point. More better alerts. Let's see. I think that's about it that I have to talk about. So thank you. That's my Twitter if you want to follow me. I don't really post anything of value, though occasionally I do post on my blog about interesting things. Yeah. So there you are. Any questions?
What sort of performance do you have in the past?
So performance or add requests?
What was the peak? What was the peak?
Peak QPS. So there was a time when we were doing about 200 QPS. It wasn't huge. At the time, we figured we were getting roughly 7 to 8% of the Twitter mobile client volume, which would imply that total Twitter client volume was somewhere in the, what is that, 15 times, so, 3,000 or so QPS, which doesn't really seem like a whole lot if you look at the Twitter universe.
What percentage of your capacity was that?
So we could serve that on 2 machines. We would typically serve that on 7 machines, just in case. Because the more machines you run, the less latency, and I suspect because of outgoing buffering, I think that if we'd have known about Nginx and thrown Nginx in there, we'd have gotten even better performance.
We also didn't know what was coming. If our business guys would tell us after the fact, oh yeah, we just signed up X client, and all of a sudden, wham, like these huge waves of traffic come in, we couldn't prepare for them, so we just kind of had to be always on the ready.
Yeah.
Well, what would you say would be the first thing you would have trouble scaling? Like as you scale this out and add more Rambo boxes, what's the first wall you would hit?
So if you're just serving requests and you don't care about the number of ads that are being posted or served out of the system, if you're just looking to service requests, the first thing that would die would be Postgres. So there's only so much you can write to Postgres, even if you're aggregating data, even if you're doing all of the right things with that, that'd be the first thing to die. Actually, I forgot to talk about Mongo. So early on in Mongo, we had been logging to Postgres, and we realized, we probably shouldn't be logging to Postgres. So we started logging to Mongo because Mongo was the new great thing at the time, and it was scalable, and it did all the great things, and you could query it, you could do all this wonderful stuff. So we started up a Mongo box, and we discovered quite quickly that Mongo's not magic. Mongo's totally not magic. It is limited by physical hardware limits, just like any other piece of software you run, especially when it writes to disk. And we only ran one of them. Mongo wins when you go and you shard the hell out of your data, and you throw it on 20 boxes. So we had a problem where we wanted to query the data while it was writing, and we were writing at the limit of the hardware, and you'd go to query it, and you'd back up your writes. And so we'd be an hour or 2 hours behind on our writes. They'd be all queued up in our ActiveMQ. That kind of sucked. So we got rid of that. We started logging to syslog, and we just aggregated them on what kind of stuff in there. And then anytime we wanted to query it, we just did a map reduce. We did like 5 or 6 map reduces because this is the kind of data you don't query very often. And that ended up being much cheaper because the map reduce is like a dime versus the $300 a month box that we had been hosting on.
How do you guard against losing your? Actually, 2 questions. First one was, there's only one Postgres instance. I think you might have answered this already in the talk, so I apologize if you did. But so how do you, since there's not n Postgres instances, you lose the one, how do you get it back?
We restore from the daily backup and maybe apply some other data. It was kind of a cross your fingers, hope for the best kind of a thing.
But you hope that most of what you need are going to be in the ActiveMQ buffers?
Sure. Also Postgres was on EBS, and the claim of EBS is that your data was there, even if the box disappears.
Lies.
Yeah, we don't believe that anymore.
Yeah.
We used to believe that.
Yeah, we're smarter now.
You said that 3 months ago?
What about syslog? How did you aggregate your syslogs? So you have a syslog in every box, right?
Right, you got we ran syslog on every box, and we ran syslog ng, which allows you to forward your syslog off to another box. And so we would forward off to a central syslog box, and then that guy would actually route the different kinds of messages that it would receive into different files, gzip the files every hour, 2 hours, whatever we had set up, upload them to S3, and once they're in S3, now we can do map reduce across them. Now we can, access them from anywhere, and now they're, 99.99999% available, all that jazz.
So in this scenario, you lose your Postgres box. You open it back up, let's call it 12 hours. You pull 12 hours worth of data from the S3 volume and push it back into Postgres and just eat the downtime while you, is that
Well,
automated?
there wouldn't be downtime is the thing. There would be no downtime if Postgres went down.
Yeah,
No,
because
so
we would,
Postgres goes down. You bring up a new Postgres box. Your backup is from 12 hours.
Right.
So how do you not have downtime? You're pulling all the S3 data.
well,
Maybe that's data loss, that's not downtime.
Meanwhile, all of those API server boxes, those Rambo boxes, they're still serving requests just with stale data.
yeah,
Gotcha.
Yeah.
So they can go as long as they want. They just, the data gets worse and worse and worse.
Okay, so no downtime, but the data is not accurate or not as accurate as it could be.
yes,
So then you push back all the data that you pulled from your central syslog server back into Postgres.
yes.
Are you billing during this time, or do you lose all those clicks because you can't bill?
So as long as you're logging off to syslog, you can bill for those clicks because you can replay all of those back to the database.
So syslog is the ultimate backup, basically.
Yeah, well, syslog to,
For at least
S3.
For the, but not, only for syslog is the ultimate differential backup. You've got the master Postgres for your core backup, and then the extra stuff you get from syslog.
We actually had backups, at least for the ad call data, from the original. Because though we had spewed stuff into Postgres for a while, and then when we switched to Mongo, we pulled all that data and we stuffed it into Mongo. And then we were logging to Mongo. And then we pulled all of that data and spewed it back into syslog. So we actually had, from time immortal, all of the data for all of the ad calls in syslog.
In order for this to be a happy scenario for Mongo, how many servers do you think you would need to have on Mongo charted?
So we were silly and we used indexes in Mongo. which isn't a silly thing because you want to be able to query your data. The problem is that every index you create, you add more I/O. And because they use B trees like every reasonable database does, you basically multiply your IOs depending on the depth of the B tree, typically by a factor of 5 for every index. Or at least, if you write a row, that's 1. If you update one index, that's another 5. You add another index, that's another 5. So we quickly ran out of scale, and so we started deleting indexes. And then once we deleted all of the indexes, then we were no longer able to query reasonably. And so the point of Mongo disappeared. Like, we didn't see a point to Mongo anymore.
But you said that you would have been okay, it just would have cost more because you needed more servers.
Sure. We stopped being able to scale just writing bare to Mongo. We could have probably gotten by with 2 or 3 at our peak load. But then that's 2 or 3 $300 boxes. So you're talking $600 to $900 to write data that you're probably never going to query. Or if you are going to query, you're going to query once every couple months.
So syslog with MapReduce is better for your database.
Oh, absolutely. We ran a $60 box a month that was our log server, and he aggregated logs for everybody. And was a multi-purpose thing because he also hosted our counter server, which wrote off to Redis and did all of our real-time counter infrastructure. And MapReduces. You could MapReduce across all of our data because even when you've got a billion ad calls, it turns out that the CPU time is cheap, and so you can buy it at like a dime or a quarter every MapReduce across all of your data. So yeah, totally cheap.
I have a question about the Rambo mindset versus the paranoia mindset, which I think is more common among systems. So let's say the scenario where you do experience the failure and you do keep your service up. So I guess it's a question of what uptime is. Like I was in my previous environment, the idea was that if it's not 100% functional, it's not up. Like how does that sound? So can you push a button? Like if you lost one of these boxes, one of the Rambo boxes, can you push a button and all the processes would bring everything back into, like pull all the data from the backup, push all that data from your syslog server, or does somebody have to be Superman and go in and like push that data through?
More than Superman, someone would have to write that code.
So in that case, do you guys do fire drills? Do you make sure that you can do it the way you expect your people to do it, or is it just from the last time it failed?
We got lucky in that it never failed. We had plans on what to do. Like, if something like this were to happen, these are the steps that we would have to take. We never went through those steps except in our Redis master failure setup. We had an EBS die on us on our database server once, but it had all of the data, so we recovered from that. There are a few other things, like minor things, but nothing so bad as Postgres goes down, takes down all of the data. We've got to jump through all these hoops to get that data back.
Did you ever test in case that actually happened? Consuming your
No,
the whole thing is, uptime.
Well, so again, uptime for us was serving ads. As long as we were serving an ad, that was up.
Okay.
Even if we had bad data, even if we lost data, it doesn't matter as long as we served an ad. That was kind of the business requirement.
That's more of a business uptime rather than a technical.
But that's
Correct.
what you architected the system around, right? Or that's why.
Exactly. That's why it was the way it was.
So when you started, how many of them were you, and did you come to consensus on how to do it, or?
So at the time when we built it, we had the same team that we have now. We've got Jeff, we had our lead dev, Eric Van Dwoestein, senior dev, Eric Van Dwoestein. We got our hair leader and senior dev, Chris Testa, at Lars. We had myself, we had Igor, oh God, I can't remember how to pronounce his last name. Do you remember?
Roshenstein?
That's it, Roshenstein. As our UI dev and all that stuff. Phenomenal. We sat down one day and we said, okay, so how can we build this thing so that we can serve requests regardless? And so we said, okay, we need to get requests in, we need to process tasks. We sat down, we put this thing together. We put together this API box.
Yeah, this whole story goes through like June to November.
Yeah, June and November, and then in December we turned it down. Like we started development around, like really started development maybe May. Like we really hammered out the design in May. We built it May, and we like opened it up mid-June, and then it was serving requests. We had Uber Twitter, who was one of our clients, and a few other people, and it served very, very well. I think we had 10 or 15 minutes of downtime a couple weeks before we turned the system down for some reason that I cannot remember. Yeah.
And again, that was 10% of Twitter's traffic on 2 servers.
Right. So we didn't serve all of Uber Twitter's traffic. Sometimes he'd turn us up, sometimes he'd turn us down and give us a different amount. We figure that with all the other clients combined with Uber Twitter, we were doing roughly 7 to 8% of their mobile traffic.
On 2 servers.
Could do it on 2 servers, though we did it on 7.
For your own paranoia.
Exactly. All right. All right. Well, thank you again, everyone.